So today we'll have 2 hours. Hopefully finish around 11:30. And actually, although there's a very scarce attendance here, this is the most important lesson of the whole course. Basically, everything you need to know and will need to know about quantum mechanics will be demonstrated in this lecture. So, in the end of the previous lecture, we have described a few of the principles of quantum mechanics, and the principles are very clear, very mathematically, very transparent if you're interested only in the computational part. If you need to compute something, it's very clear what you have to do. So some people have gotten to a point that describe quantum mechanics as shut up and calculate. Don't bother about anything else, so and so you won't understand it. On the other hand, we are physicists. We want to understand what does it describe, what does it tell us about reality. The unfortunate point here is that there's no agreement, and worse, there's no prescription how to validate any one of these approaches or descriptions to show that that's the true interpretation of quantum mechanics. I guess all of you have heard about different interpretations of quantum mechanics. What is the most well known? The Copenhagen interpretation. Anyone who saw a movie in the last couple of years had to hear about the many Weld interpretation. And there's also Bohm's picture about quantum mechanics. The fortunate or unfortunate conclusion about all those descriptions is some of them may sound to you personally a better description of reality, but unfortunately we have no experimental way to differentiate between these interpretations, and therefore no real way to decide which one is correct, or perhaps something completely different is correct. So I'll summarize what we know about quantum mechanics again. It was actually described in the end of the previous lecture. First of all, wave function or a state in Hilbert space describes everything that we can and need to know about the situation of the physical realities that we are trying to describe. Okay, so what is this wave function? Well, different interpretations. One interpretation is that's reality. The fact that you don't see wave function, but you see something else around you, is a problem of your interpretation of what you're seeing, but reality is the wave function and the Hilbert space in which it exists. And for some reason, that's not exactly what you feel. Is it because you're a macroscopic entity? Is it because the way that evolution formed you? Should pick, probably there's thousands, if not tens of thousands, different popular and semi-popular and non-popular books about it. Okay, the other thing is basically the Copenhagen interpretation, which tells you, look, this is some prescription how to calculate interesting quantities, things that you can measure. It's a tool. It has no meaning by itself. Why is it this tool, and what is the deeper reality that sits behind it? You can't approach it. So you see why you can't differentiate between these two interpretations, because both of them tell you you want to know what is the result of an experiment, take the wave function, treat it mathematically, you'll get a result, and that's what you measure. What is the meaning? We have no measurement device that tells us what is the meaning of these things. Now, I'll mainly describe here what we are doing in quantum mechanics in the terms of the Copenhagen interpretation. Not necessarily that it's the best interpretation. It has huge logical holes in it, and I'll point them out, but it's the simplest, and I would say that if you start in quantum mechanics, the easiest to integrate into a way to solve problems with it. Perhaps that's the reason that historically it came out first. It has problems in consistency and logical foundation. So basically, what happens in when we're trying to describe an experiment? Okay, you perform some experiment. You perform a measurement. Now, what is exactly a measurement? Again, hundreds or thousands of papers and books. What constitutes a measurement? But let's treat it now heuristically. Something that you look on your device and see some numbers that comes out of it. Okay. So, according to the rules of quantum mechanics that we described in the previous lecture, it tells you that the wave function at the point of the measurement was at an eigenvector of the operator which describes this measurement. And therefore, I know exactly what is the wave function immediately after the measurement. Okay, so I have my initial condition. You remember that I described that you start from some initial state, and then I'm telling you, I told you basically we'll speak about how is this initial state determined. Now I have the answer. You measure something. You measure something, you read the result, and if the measurement is a good measurement, you can write down what is the wave function immediately after the measurement. Now, usually what happens at t0, you know. You want to see what is the development in time. You are going from t0 to t. Great. Then it tells you, oh, no problem, I have an equation for you. For a single particle, non-relativistic particle, it's the Schrödinger equation. For more complicated stuff, it's the appropriate adaptation of the Schrödinger equation for describing this system. Basically, you should write a Hamiltonian or a Laplacian of the system and crunch the result. There's different ways how to crunch the result, from simple solving of a differential equation till path integrals, but all of them are mathematical tools to give the answer on how to solve this equation. And basically, it's a very simple equation. whatever your Hamiltonian describing the system. Now you should have stopped me and told me one moment. How do I define my Hilbert space? And from where do I take this identification of a specific mathematical operator as something connected to a measurement? So my answer is only hands-on experience. There's no mathematical way to prove that something is a Hilbert space. What do I mean? You go and perform a measurement. And I'll describe in a few moments a specific kind of experiment, the easiest kind, where we have a Hilbert space of size 2. Size 1 is not interested, nothing can happen. Okay, but we have prescriptions. H, we said you take the operator of P, square it, divided by 2m, you have a Hamiltonian of free particles. What is P? What is the operator for P? This identification you just take from classical mechanics and believe that it continues to work. What is the definition of P? Okay, that's minus IH bar dot to the x. Why is that? I can't give you a few arguments. I can't prove you that this is. It is connected with the fact that momentum is actually comes out from conservation of a symmetry of translation, and derivative according to x is moving by a bit. And we had to add our I because otherwise it's non-Hermitian. Okay, why it's exactly H bar there? Because it works. Okay, so we go and develop the wave function according to the Schrödinger equation. We have a full. You hear all the time that quantum mechanics is non-deterministic. Well, it's very deterministic. If you want to look on quantum mechanics, on reality, just development of the wave function, I gave you an exact prescription. It's completely deterministic. Now, but they tell you, well, it's a question about determinism of measurement, right? If I measure something, it depends if the basis of this operator changes with time or doesn't change with time, according to this guy. We'll find a mathematical description to answer this question. Will be called the commutation relation, but we have a prescription to do it, and the answer is some results will depend on time and be non-deterministic. Some results will be completely deterministic. If H has no implicit variable of t in it, doesn't depend directly on time. If I measure the energy at time t0, I know that it will continue to be the value of energies that I'll measure at time t. So depends on what you're asking. Okay, so this part is deterministic. Now you perform a measurement. Perform a measurement of some specific operator. What do you do now? Okay, you cranked psi, you got psi at time t. N could be finite or infinite, depending on what is my Hilbert space. I write my wave function at that time as a superposition according to the basis of this operator at this time. You want to know what is the probability of measuring a specific value. Can I tell you which one of the values that are not equal to 0 will I measure? No. This is non-deterministic. Now, in the Copenhagen interpretations, they just sweep it under the rug. That's what happens. There's no, you can't even formulate the question, why is it like this? It's a meaningless question. That's reality. Go home happily. Now, when I say probability, what do I mean? If I do this experiment only once, I'll get some value and won't be any cleverer. Do I know that there are other values that could be here? Can't answer. I did one measurement, I got one result. But if I repeat, go always to the same initial state, go the same development in time, perform the measurement, I'll get here a distribution of probabilities. I'll know exactly the amplitudes of the wave function at time t according to the basis of this operator. So basically, it's a statistical description. I can't tell you what will be the result of a specific measurement, but I can tell you that if you will repeat your measurement again and again and again, you'll get this distribution. Now, this point was basically a red flag for Einstein, for example. He's a leading, perhaps, physicist that emphasized this point. Well, we have another example in physics where that's what we're doing. Thermodynamics, statistical mechanics. What's happening there? We have a container with a lot of molecules. They bump into each other. They transfer energy. If we'll open a small hole and ask, what is the velocity of a particle coming out of this container? All I could say is there is some distribution of velocities for the specific for the specific molecules that comes out, I'm unable to answer, but if I repeat it again and again and again and again, I'll get a distribution. You did already statistical mechanics. No. It's known as the Maxwell distribution. Maxwell, when he wasn't busy with doing electromagnetism, also gave important contributions to statistical mechanics. One of them is writing down the distribution of exactly this problem that I described. Okay. Maxwell, of course, is much before quantum mechanics. What was the picture that Maxwell had in his head? His picture was, look, there's 10 to the power 23 molecules in this container. In principle, I could have written down the equations of motions of each one of them, solved it, and tell you exactly if I knew the initial condition, I could have told you exactly what will be the velocity of the next molecule coming out, because it's deterministic. But one, I'll never have the initial condition exactly. Two, I don't really care. Three, it's computational, too complicated to solve 10 to the power 23 equations of motions and get the distribution. Therefore, I go to statistics. So nature is not inherently statistical. Just the way that I ask the question and the amount of resources that I'm interested in investing into finding out what is the answer pushes me to go to statistical results. So it's not inherently undeterministic, but it's because of my decision not to probe too deep into this problem, because I can't, because I don't, sometimes it's just I don't care. Most of the time when I'm letting out gas from a container, I want to know the average velocity, perhaps the distribution. I don't care what each molecule does. Too much information, who cares? Okay, so Einstein grasped the behavior of quantum mechanics as basically the same statement. There's a deeper theory, it's known sometimes as hidden variables theory, that is behind quantum mechanics. But since we are not clever enough to formulate it, we're stuck with some statistical description, but nature by itself is deterministic. Now, someone heard about Bell inequality or Bell's experiment? Okay. We'll perhaps do it towards the end of the semester, but at the moment all we have to know is there's some basic difference between this description and a classical probability description. What is the heart of this difference? Basically, that probability is pulled out from the amplitude square, but the time development is on the amplitudes. So it's not a classical development of probabilities. You have here much more information because you're not, in principle, the time development of the amplitudes. You can see that you can get many probabilities out of different amplitudes. Think if A is different by some phase, you won't see here any difference. So then basically you can describe an experiment where any form of classical probability will give different results from this prediction, and that's Bell inequality, that's the probability of measuring something. As I said, perhaps we'll touch upon it towards the end of the semester, perhaps not, is different than the classical. You, lo and behold, you go to nature, perform the experiment, and it tells you that you can't describe it by any classical model. Just the results of the experiment fit quantum mechanics, don't fit a classical description. Now, people that like interpretations of quantum mechanics are clever enough to overcome this problem, and they say, yes, if the probability depends locally, or if the probability is a Markovian process. You discussed Markovian process. Markovian process is a very simple assumption in probability, which tells you you want to know the probability in the nth time step. You need to know the probability of all steps in n-1 step. You don't need to know anything about the past. That's a Markovian. Let's say when you're throwing a coin, the chances of it falling head or tail doesn't depend on what happened in the previous flip. So it's no memory. And if you decide that your classical probabilistic description is Markovian, it can't describe. You can put in some effort and come up with some formulation that your probability doesn't depend only on the previous moment, but on the whole history. Then you can reproduce it. Then you have to get to a point where you have to swallow the very bitter pill of telling that the system somehow remembers previous instances and it has an influence here. Similarly, in philosophy, you can say that if the system knows what happens everywhere at the same time, non-locality, you can again correct. And then you have problems with relativity. But however you want to swallow your poison, you will swallow poison here. You can't give a simple, intuitively descriptions of probabilities that you want depends on the probability here in the previous moment, not on the probabilities everywhere, not on the probabilities in any previous time. If that, only quantum mechanics gives you the answer. So, you perform the measurement. You measured 07, the seventh eigenvalue of this operator. Plus, that's immediately after the measurement. procedure of quantum mechanics. We'll spend a lot of time on solving Schrödinger equations for specific systems. Free particle, particle in a box, a particle in a harmonic potential, a particle in a Coulombic potential, all of them very interesting physical systems. But at the end of the day, that's what we're doing. We'll discuss finding bases of all kinds of operators because it's very important in order to tell what are the possible measurements. Again, a mathematical point. From the point of view of physics, all you need to know is the operators that interest you, what are their eigenfunctions and eigenvalues, what is the initial condition, how does it develop in time, that's that. In Copenhagen interpretations, they call the things the wave function collapse. Why? Because until here it was built out of a superposition of many states, could have been, not necessarily. Here it's only one component. That's a collapse, again and again. And this collapse is non-analytic, and I can't give you any prescription to find out on what exact value will it fall. I can only tell you probabilities. That's it. Quantum mechanics, closed and wrapped.
Once it did go to 07,
Right.
The next time you'll measure it, it'll definitely be 07 again.
No.
But it's
Depends on how H influences the components of this operator. It's not necessarily that the development in time will preserve the system or in. Okay, it's a good point to put in what happens for development in time. Let's be specific. Okay, so another way on looking, it's simplified, assuming on H time independent. Okay. Now, in your undergraduate, most of the time this is what you'll see. To a point that when you come into systems which have time dependence, like let's say in quantum optics, where the wave function, where you have electric and magnetic fields that change with time, you will stop a minute and get confused because you're so used to this language. But we are using it in the undergraduate course most of the time because it's the simplest and most elegant way to describe it. Okay, so if I have a state, some state at t equals 0, let's say, after I measured this guy. And I'll write it down in the basis of the operator. So this is the basis of H. We solved Schrödinger equation for the case that we have time-independent Hamiltonian. What did we learn? We learned that the wave function develops with time only in the phase. So, conclusion, psi of t is equal to okay. What does it tell me? If operator O and E share the same basis, so I'll have here a specific value of the energy state, then it will stay on the same wave function up to a phase, because then I don't have a sum, I have just one. And I'll return and measure O in some time forward, I'll see exactly the same measure. If O, the eigenvalues of O and the eigenvalues of E don't share the same basis, so I'll have here a superposition, and the amplitudes of each member in the superposition depend differently on time because they have different energies. I will get a different result in a future time. So, how do I find out the two operators have the same basis or not? That's a commutation relation. And we'll define it, see the mathematics, explain exactly what stands behind it, but the idea is simple. It shares the same basis as the energy operator. There will be no time dependence, and you'll measure it in a future time, you'll see the same thing exactly. It doesn't share. The fact that you measured at some time, some value doesn't guarantee that you'll measure it in the next instant of time. Yes?
You assume. Well, from to specific value.
Exactly. I go from a case where I have superposition of basis states to one.
Yeah, but to where we do in this where we do it.
Okay, this is another famous case that we will hopefully discuss towards the end of the semester. That's exactly EPR. Einstein, Podolsky, Rosen, and the whole story of entanglement. Let me explain. The whole confusion there and the fact that Einstein holds that this is theory influencing the distance makes no sense, comes from the following thing. And I'm not doing it at the moment, although it's very important because it's a property of more than one particle. At the moment, we know how to treat only a single particle. But the point is, you have a wave function that describes two particle states. What does it mean? That I can explain. A two particle state tells you that it's one system. We told that the wave function describes the whole physical reality. So if in my reality there are two particles, the wave function will describe the whole properties of the two particles. Let's say that spatially the two particles are far from each other. I measure a property of one of them here. That will collapse the wave function, and meaning that it will tell me something about the behavior of the particle somewhere very far away, although they had no time to communicate. And many world interpretation will tell you what's the problem. Reality is not this real space description, it's Hilbert space, and in Hilbert space that's a state, and all is well. I don't care that this state tells you something about what's happening here and there.
Yeah.
So basically the collapse holds the difference, the huge difference between class. You could stop and tell me in the beginning of the course, well, why do we have a course in quantum mechanics? We learned waves, right? Right? And the broadest picture is that quantum mechanics is just wave nature of the electron. But we know to solve wave equations, we know everything about waves. Just let's work with describe quantum mechanics as a wave phenomena, and a lot of time in popular literature you hear that quantum mechanics is a point that it's a wave. And that's it. Why do we need a special course about quantum mechanics? The point is exactly the measurement. Here comes in a popular language this wave particle duality. What does it tell you? I had a wave. Okay, developed in time, great. Now I measure a position. Position will give me an answer, there's a particle here, or I don't have a particle here. So suddenly, instead of in classical, when I measure a wave here, it doesn't say anything about the wave somewhere else. It continues to be a wave. Here, once I measure and see that the particle is here, it's not there, because it's in an eigen function of the position operator.
Right.
And that's exactly the collapse, the wave particle duality, and so on and so forth. I very much prefer to swallow these type of ansatz or assumption from the beginning in a very clear-cut language, and then discuss all these popular concepts, because all of them, all the questions are in this procedure. They come out from this procedure. And doesn't matter if you accept them or not, you feel comfortable with it or not. Once you know to work this algorithm, you know quantum mechanics. You're able to calculate, perhaps also shut up. But all the paradoxes and unintuitive are hidden here. It's not that you have to stop and think about this problem again and again and again for different systems. Is light a wave or a photon? Is electron a wave or a particle? All of it is hidden here. Okay, so let's see a specific example of a simple, with parentheses, experiment that demonstrates everything that we need in order to treat a quantum mechanical system. The Stern-Gerlach experiment. Stern and Gerlach, two German physicists during the 20s and 30s, they performed an experiment that changed our understanding of the properties of electrons or particles in general. And it's one of the most simple and elegant demonstrations of quantum mechanics. I don't know much about Gerlach. Stern. Otto Stern is a legendary figure in physics. A lot of stories about the guy. He was Jewish. I'm not so sure about whether he was a converted Jew or not, but when the Nazis came into power, he had to leave Germany. He lost his lab. He was an experimentalist, of course, and one of the interesting stories about him, he after leaving Germany, started working in Carnegie Mellon in Pittsburgh, the US, and built his lab. Suddenly, the management told him, we can't open your lab before we have a safety inspection. Safety inspection, I never heard about it. I was a professor in Germany for 20 years, never heard about it. Sorry, here we do by the rules. So comes this safety engineer, goes over his lab, tells him, look, you have here exposed electric cables that carry 800 volts. I can't authorize opening such a place. Why? Because it's dangerous. Well, I have much experience. I'm not worried about it. Yeah, but you have graduate students that come to do experiments. They may be harmed. The Stern tells this inspector, or at least that's a story, and do we really want to keep alive a graduate student that's unable not to touch an exposed electric cable? Anyways, the other very famous case is he invented the Pauli effect. Pauli, which is the one that wrote down the mathematical description of this experiment, was a visitor in his lab. Any time that he came to visit, something in the lab broke out. So basically, Otto Stern termed something breaking up as the Pauli effect. Now, one day, Otto Stern was in Hamburg, I think, and he came in the morning to the lab. All kinds of containers broke up and whole mess in the lab. Asked his student, was Pauli here? No, it wasn't anywhere. No, it can't be, it's a law of nature. He phoned up Pauli, were you in Hamburg yesterday? No, but I was on a train that came from visiting Bohr in Copenhagen back to Munich, where I was. What time was it? Exactly. That's the explanation to what happened in my lab. Okay, so what was the experiment? Okay. You have a container, very similar to the container of gas that we discussed in the beginning of the lecture. Now, you heat up this container, open a small hole in it. Particles come out. You put screen on the other side. Of course, there will be some small deviations from because of the size of the hole. But if you just heat up this container, wait some time, look on what you see on the screen, you'll see a deposit of these particles sticking to some region of the screen. Okay, no fancy electronics, nothing too complicated, just looking on where these particles hit the screen. So you put the screen, run it for a few hours, you see a smudge of deposited particles on the screen. Lovely. Now, this is a technique that is still used today to deposit stuff, and today they can control it, so you'll get like a single monolayer of a given substance, and then let's say switch the source to another atom and get another. That's a well-known way nowadays to build up all kinds of design materials. In Aviad Friedman labs, they have a machine that does exactly this type of stuff. Okay, lovely, boring. Now, you have atoms that are magnetic. Why? We'll be able to answer the why question in a few lectures, but at the moment, a fact of nature. Okay, so you think about your particle coming out of this container as something that has velocity and has some magnetic moment in some direction. What is the direction of this magnetic moment? Well, it's random. We have no way to control it, or at least you'll see that we do have, but at the beginning of this experiment, Stern and Gerlach didn't have any way to control it. Okay, now put some magnetic field. I don't want even to get into too much details. It has to have a gradient in order to pull it, but you can understand that if you put some magnetic field here, the motion of this particle, this atom, will depend on the angle between its magnetic moment and the field. Okay, so you turn on B, what do you expect? The smudge will be elongated because it comes in different directions. They'll have a different force applied on them, and we'll see a widened smudge of particles on our screen. First thing that we want to understand here about an important lesson about quantum mechanics is, well, what is measurement? I come after 2 hours and look at my screen. What do I measure? I don't measure the velocity of the particle because I don't know in what velocity it hits the screen. I don't describe what's happening on the wave because basically I don't know. I know where it hit. But my measurement is of the direction of this magnetic moment. Because then I look at the shape of my smudge, and I can tell you what is the size and direction on the average of this magnetic moment. Okay, so Stern leaves his lab in the evening, sets up his experiment, comes back in the morning, and lo and behold, he doesn't see this and doesn't see this. Sees 2 points. Okay, from spectroscopic data that Pauli has analyzed a few years previously, it was known to people who are trying to describe atomic behavior that there are properties of the atoms which depend on the moments that gives me always just 2 values if I try to measure. Okay, so what did we? Well, that's not what they did because they didn't have this whole mechanism in space. But what do we want to pull out of it? Well, we want to tell us that our description will be able to tell us something about the properties of my measurement. I'm not interested in psi of r because I didn't measure it. I'm interested in the directions of the of the magnetic moment, and experiment comes, pulls me in my hair and tells me there is only 2 values that can be measured. I didn't anticipate it. I didn't have a good argument why it should be. So the same as I had no good argument why the spectrum of the hydrogen atom should be discrete. Why not any wavelengths coming out of it? Here I have an even simpler situation. I have only 2 values in this measurement. Return again and again and again, send millions of atoms, and again, it's always concentrated in 2 smudges. There are other atoms between 3 and 4, but for a specific type of atom, some of them give me only 2. What do I conclude from that? First thing, according to all the principles of quantum mechanics that we have studied, I know that the size of the Hilbert space, which is relevant to the description of the magnetic moment, is 2. Why? Because measurements pull you out on basis states. I have only 2 basis states. Why only 2? Because that's the only thing that I measure here. And therefore, I know that I have the size of the Hilbert space. Which is the smallest Hilbert space that can give me some meaningful development in the system. Okay. Well, I broke symmetry here. I put a magnetic field in some direction. I'll rotate it. These 2 smudges will follow it. So basically, I know that by putting B only in the Z direction, I know that I'll measure only 2 possible directions of the moment. One in the direction of the magnetic field, one in the opposite. So, I'm trying to construct an operator that will describe this 2-dimensional state. Okay, so let's define our basis state as 1, 0 and 0, 1. Why? Because why complicate something that I have no reason to complicate? Complicate stuff is not a virtue by itself. Okay, what do I want here as a result of a moment? It's either in the direction or in the opposite direction. And at the moment I could add the units of the moment, but at the moment I'm just looking on the bare bone description of the Hilbert space, so I won't put in any additional physical quantities here. Okay. and I'll call y. These are eigenvectors of this thing. They give me two values of eigenvalues, plus minus 1. That's a description of my state. Okay? Now, if I dig a bit deeper into my mathematical knowledge, can say basically on a 2 by 2 matrix, how many independent matrices do I have here? Four. Simplest way to think, I'll put here A, B, C, D. A0, 0, 0 plus B will be a basis in this matrix space. Okay. Spare time, you can convince yourself that you can build from these 4 matrices any 2 by 2 matrix. Now, these guys are known as Pauli matrices. Okay, so what are these guys in a moment? They will correspond to something physical that can be measured. But let's ask ourselves, how do I demonstrate the things that I said before about the system? Let's take our experiment and complicate it a bit. Just take this guy and make slits at these 2 points. Okay. Put an additional magnetic field. And put a screen somewhere further on. Someone can guess what will I see here? I have now 2 sources.
3 dots.
3 dots. Any other guesses?
4.
4 dots. Bernal's pattern. That proves that intuition about quantum mechanics is built with time. Actually, why? Basically, this guy, for this source, what will be the direction of the the moment of the atoms that went through this slit. Only in the up direction. So I'll switch here from 1, 0 into the language of up, and 0, 1. So it takes less space in the drawing here. So this guy basically has only one component. They came out here in some superposition, but the fact that it came out from this guy tells me that it's up. This guy comes out with that. So the continuous separation according to B, here I have only electrons with spin up. Therefore, the smudge will continue to be one smudge because I don't have any components of down. And here I have only down, no ups. And this is a case, for example, I measured once. How did I measure? By doing a hole here and letting only electrons come with an up spin to continue. I could have blocked this guy, for example. And this, all the electrons are in the up state if I write down the Hamiltonian, which I haven't yet defined. It will continue to be in the up direction, and that's it.
So it's kind of like saying that
I measured here on the slit, and it will continue. If I continue to measure it at a further time, it still will be up.
that means, if I understand correctly, that the eigenvectors are the same eigenvectors
As the Hamiltonians it describes. Now, okay, a very important experiment. Now let me complicate somewhat this. Instead of putting the magnetic field in the BZ direction, I'll put it in the BX direction. And now I'll give my screen a bit of a three-dimensional, two-dimensional. How many smudges will I see in this case?
Still two? No, four. Four. Oh, A.
And so I'll get okay, let's give the quantum mechanical explanation right where I see here for. Okay, I have to say what is the basis that describes the x direction. Here I have a bit of intuition. I know that 2x2 matrices are broken up to the identity matrix. It probably doesn't signify anything. and additional 2 matrices, operators that can play. I guess one of them is Bx, one of them is correspond to Bx, the other one to By. Okay. Let's assume that sigma x is this guy. As I explained previously, once I establish the dictionary, any combination here of the experiment be in the direction between x and y, anything I can describe in this system. Okay. What can I measure here? Of course, the eigenvectors and the eigenvalues of this operator. Not leaving this complicated and strenuous exercise of diagonalizing and finding out the eigenvectors and I'll just write them down. I assume that all of you can perform the mathematics of finding what are the. So I'm putting here y1 over square root of 2 because I need normalization. Lo and behold, so this is an eigenvalue with an eigenvector with eigenvalue 1. So here's the eigenvalue is -1. Are they orthogonal? Yes, sir. Are they normalized? Yes. Great. I know the basis states and the eigenvalues of sigma x. Now, at the point of measurement, I had here a state 1, 0. Why do I have the state? Because I measured it. I know it comes out from the upper smudge. That's a measurement. Now I want to write it in the basis of the x. Is it correct? Almost. I'm missing here a factor. No. Sorry. Complicated algebra, but it works. Okay, I'm getting 1, 0. So now, with no further calculation, I can tell you, I'll measure here two values. Why? Because in the x direction, I have this wave function is a superposition of two. With probability 1 over square root of 2 squared for each component, which means half. So half of the cases it will be on value 1 of sigma x, the other will be minus 1. Exactly what's shown here. Now I can continue and amuse myself with putting here a whole series of slits in different directions with different directions of the magnetic field. That's exactly Bell's experiment. Take two particles, do something here for one of them, measure the other one on a different angle, and write the probabilities of measuring something. And these probabilities can't be described by classical probabilities. That's all. So, basically, that's all we need to know about quantum mechanics. Unfortunately, the bases will usually be more complicated than size 2. We will have to write down the Hamiltonian and give a full-time description, but the procedure is the same. Know your Hilbert space, know the eigenvectors of the things that you want to measure, describe the measurements using these eigenvectors, and you're able to answer any question about the probability of measuring any quantity connected to these systems. Now, what we will do in the next lecture is, once we move into continuums and try to write down the eigenvectors of two of the most well-known operators, position and momentum, we'll see that we're running into mathematical problems, but as good physicists, we'll sweep it under the rug, use some definitions of Dirac, which were developed in order to give mathematicians fits. They're not well defined until today's era. But it gives you a very workable way to describe also all these procedures that we have encountered in continuum. In discrete Hilbert spaces, everything is very well defined, you can work. Therefore, in complicated quantum mechanical problems like quantum chromodynamics, doesn't mean anything, but it's a quantum theory that describes the behavior of interaction of quarks confined in protons and neutrons. You have no idea. The problem there is that if you try to work in continuum, life is very messy, but if you go and write it down on a lattice, meaning you turn infinite continuous space into lattice points which are discrete, mathematics becomes much clearer and the procedure much easier, and most of the calculations that people are doing research in this field are done on lattice quantum chromodynamics and taking some limit. Same thing for field theory, like quantum electrodynamics. So a usual procedure in order to avoid all these mathematical problems is work on a discrete system and take it to infinity and hope mathematicians will tell you that you are not doing the take it to infinity correctly or well defined, but anyway you can pull out results out of it, and these results work wonderfully exact. So we'll do it in the next lecture, but as I said, you all know at this point everything that you should know about quantum mechanics. All others are examples, digging a bit more deeply, like how can you say immediately if two operators have the same basis or no, that would be the commutation relations and all kinds of things like that, but everything works according to the logic that I described. So see you next lecture, which will be the usual time. Thank you.
הזכרתי בעוד, כאילו, זה לא בדיוק קשור, כי הסברת את כל מה שהיית צריך לעשות בהרצאה, אבל יש איזה ניסוי שנזכרתי בו שהוא גם